All right, so we're happy to have Olivier give his final lecture on the general relativistic Boltzmann equation with applications. And apologies to everyone about the inclement weather, but you get the full Toronto experience. Yeah. All right, so take it away.
Okay, thank you, Jakov. Yes, yeah. So sorry about that. It's just a day I was thinking about using the Blackboard for some things. So let's see how it turns out. Um, all right. So okay. So please feel free also to interrupt me at any time because I can't see you. So just unmute your mic and make your question. So so the plan for today's lecture is to discuss some of the properties of this first order fluid theory we derived in the last lecture. So this was based on this Chapman-Enskog approximation of the relativistic Boltzmann equations. Um, so so the first thing we're going to discuss is the hyperbolicity and causality of this theory. Okay, so for this, we're going to linearize the system and look and basically do linear algebra things. But I'm going to motivate the more general result, which was in the nonlinear case. So I'm going to tell you about a result where we can prove a well-posed Cauchy problem, at least locally in time for this theory. And then, okay, here I'm not going to present the details, of course, but just tell you more or less what has to be done. Then we're going to ask about the stability of global equilibrium, and this will be restricted to Minkowski space. So remember, we fixed the background. So the background, we don't look at self-gravitating fluids in this course. So we're just asking if this just the fluid perturbations would be stable. And for this, we're going to do a mode analysis. Okay, and we are basically going to show that it's possible to choose the parameters in our theory such that all the modes, well, except the zero mode, decay in time. And finally, I'm going to finish off with some comments on the entropy production. Okay, but because you remember in the Boltzmann, for the Boltzmann equation in last lectures, we showed that there is a relativistic generalization of the H theorem. So there's a entropy flux you can write down, and if the distribution function is a solution of the Boltzmann equation, then this has non-negative entropy production. So now we have this fluid theory, and of course this is not exactly the Boltzmann equation, but it was obtained by a truncated approximation, and so we cannot expect then that we have that this truncation will respect this exact non-negative entropy production, and in fact we will see that this is what happens. Okay, so I will finish off with some comments regarding this. So in principle, this talk is self-contained. So if you haven't been to almost self-contained, except for some things I'm going to say for the entropy, but for the remaining things. So if you haven't been in the other lectures, you can have a fresh start. So I haven't understood the last lectures, you can have a fresh start. So for this, I'm going to recall the theory we derived, and then we're just going to, you can take this theory like as given to you, and we're just going to analyze its properties. Okay, so the first order theory that we derived in the last lectures is the following one. So it's described by the balance laws. Okay, so the divergence of J mu is zero, the divergence of T mu nu is zero. So T mu nu is a stress energy tensor, is symmetric. J mu is a current density, and the current density you can always, it's a future electric time-like, so you can always decompose it with a unit time-like vector field U, and the norm n is a particle density, and then T mu nu you can always decompose in this way. Okay, so this little e here will be the energy per particles. This epsilon here would then be the off equilibrium contribution. Q would be the heat flow. P is the pressure. And remember, I told you yesterday that we impose this trace fixed particle frame. So that translates now that if you took the trace of T mu nu, then the off equilibrium configuration, the off equilibrium contribution, sorry, will be zero. So that's why here you have epsilon to the third, which then cancels this epsilon when you take the trace. And tau mu nu, which is orthogonal to U and traceless. Okay, and then to close the system, then you have these constitutive relations. Okay, so this is so how you write epsilon q, did this off equilibrium contribution, epsilon q and tau. Okay, and the easiest one is tau, so this is related to the shear. So let me blend this in. So here are the definitions. So this delta here, that's a projector orthogonal to U. Sigma would be the shear associated to the for velocity U. Theta is expansion. Okay, so this tau would be -2 times some coefficient times sigma mu nu. This is the expression for the heat flow. Okay, so d mu t would be the gradient of t in the direction orthogonal to U. A is acceleration. And this is the expression for the perturbation of the energy density. Okay, so this coefficient kappa, zeta, and eta, they are related to the thermal conductivity, bulk viscosity, and shear viscosity. So you can compute them from kinetic theory, as I showed in last lecture, but now you can think of that they are given to you, they should be positive. Then another important thing for what we're going to do now is that you have also these additional coefficients, capital gamma 1 and capital gamma 2. Okay, and they were unspecified. So I showed you last time that in principle these are free parameters that you can use, and they're not supposed to change the physical content of your theory. Okay. Now this CV here, that's the heat capacity per particle, and H is the enthalpy per particle, which is related to the energy per particle in this way here. Okay, so this is the review of this theory we derived last time, and also this equilibrium configuration. There's also E and P. They are not arbitrary. And but they are related. So P, you have the ideal gas equation of states. So P is n kBt. Kb is the Boltzmann constant, and then H and E, they are functions of Z, which is basically the inverse temperature. So it's m over kBt, and they can be expressed analytically in terms of this modified Bessel functions of the second kind, okay, which are given by these integrals here. Okay, and now the first exercise for today's lecture is because we're going to use this at several places, so you can prove that the energy density per particle, the enthalpy per particle, and CV, which is the heat capacity at constant volume, and CP, that's an error, sorry, that should be H here, not P. So Cp is dH by dt. They are monotonically increasing functions of the temperature, and they satisfy the following inequalities. So E and H, they are between m, which is the mass of the particle, and infinity, and Cv over Kb varies between 3/2 and 3, and Cp over Kb varies between 5/2 and 4. And actually, these lower and upper bounds are attained in the limit when the temperature goes to 0 or to infinity, respectively. Okay, so I mean, if you want, you can just plot these things and then just check during inspection that this is what happens. But you can also generalize this to arbitrary dimension and prove that this is actually true in arbitrary dimension if you replace the free here by d, the spatial dimensions, and cp over, and this will be d plus 1, d half plus 1, and d plus 1. Yeah. Okay, and as I said, these quantities here that describe the off-equilibrium contributions. And for what follows, however, so we're not necessarily going to assume that E of t is given by exactly these expressions. They could be also a more general function of the temperature, but if it's supposed to describe a simple gas, then it is given exactly by these expressions. Okay, but in principle, it is what I'm going to say is more E could be an arbitrary function of the temperature with some certain restrictions I'm going to mention later. All right, so all right, so now, okay, another comment what I want to make is that I mean, in the physics literature, so there's like a recipe to use this Chapman-Enskog approximation, which says that you should eliminate the time derivatives. So that would correspond here of choosing gamma 1 and gamma 2 equal to 1 exactly. This would eliminate t dot here and the acceleration here. But in fact, there's no reason to do so, as we showed last time. And actually, for what we're going to do, we're going to assume that this is precisely not the case. Actually, it is not. For hyperbolicity and so on, it is not a good idea to choose this equal to 1. All right, so now let me now analyze the evolution system that we obtained from this fluid theory. So we're going to assume, as I said, that gamma 1 nor gamma 2 are equal to 1. And what you can do then, so you do something which sounds a little bit strange maybe, but you use actually the first constitutive equation. So if gamma 1 is not 1, you see that the coefficient in terms of t dot is not 1. So what you can do then is you can use this equation as an evolution equation for the temperature. And likewise, this equation for the heat flux, you use, if gamma 2 is different from 1, you can use as an evolution equation for velocity. Okay, and then you use the balance law as evolution equation for the remaining quantities. And if you do this, then you get the following system. So this is the system of equation you get. So this is the first one is just a continuity equation. Then this is evolution equation for the temperature. And alpha 4 and alpha 5, there are now these coefficients which depend on gamma 1. This is the equation for the acceleration, I mean for u. And here you have 3 coefficients, beta 1, beta 2, and beta 3, which depend on gamma 2. And then from the balance law, then you get these 2 equations, which are taken as evolution equation for the energy density, the off-equilibrium contribution of the energy density, and the heat flow. Okay, and now the first comment one can make is that this system is actually, I mean, it's first order in time, I mean, at least in the dotted quantities, but it is second order in space. And this is due to the fact that here you have the shear that appears, and the shear depends on first derivatives of the forward velocity. Okay, so this equation is second order in space, as second order spatial derivatives. F epsilon, F q are nonlinear terms, which are given explicitly by these expressions. And also depend on gamma 1. Okay, and now we would like to analyze if this system describe a well-behaved evolution, say. Okay, so the first thing that you can do to get an idea of what is going on is you can start by linearizing the equations. So more specifically, we're going to assume that the background is Minkowski. just to make things easy. And that will linearize about a global equilibrium configuration. Okay, so we assume that n is constant, and I'm going to call this constant n0, that the temperature is constant, T0, and the forward velocity is constant. And by your boosts, then you can always achieve that it has this particular form. Okay, so more or less, if you have a smooth background metric, which would not be Minkowski, then, I mean, well, Posen's is about the high frequency mode. So the intuition is that you look at high frequency perturbation, and then if you zoom in a small region, then basically, if you have a smooth background solution, then it looks like constant. So this is the intuitive justification that this might tell you the whole story. Okay, but now let's think of it that we linearize. Okay, the system and so here's the linearized system. So here, so now by an abuse of notation, n and t will denote also the first variation of n and t. The forward velocity, because it's the first variation, should be orthogonal to u. So I can parameterize in this way, where v is a free velocity, if you like, and then q would denote the first variation of the heat flow. Okay, now so you plug this into the previous equation, linearize, and then you get the following system of equation. So it is here you see explicitly now that it's second order in the space derivative, so the Laplacian on v that acts here. Okay, and then you get something from these terms here. All right, and now, so what can you do? So the first thing you can do to get a quick idea of what could go wrong, let us look now at the vorticity. So for the vorticity, I take the curl of this equation here. So if I take the curl of this equation, then I see, I mean, because beta 1, beta 2 now are constants. So if I take a curl here, this goes away, this goes away. And so I get beta 3 times the curl of Q. And now if I combine this with the curl of the last equation, okay, then you see I get a curl here. So I get this term here. This goes away because it's a gradient. This goes away because it's a gradient. And from this term here, the first two, they vanish because they are gradients. And here appears the curl of Q. So in the second equation, I can now eliminate the curl of Q. Okay, and then I get a second equation, so second order equation for the curl of V. So summarizing, I mean, if I define the vorticity as the curl of V, okay, then I get this second order equation here. Okay, and beta 3 here is this coefficient here. Okay, and now just by looking at the terms with the highest order derivative, which will be this one and this one here, you see that to have a, I mean, to have a well-posed system, then certainly I need that eta beta 3 is larger than 0. Okay, because if it's, I mean, actually it should not be negative. If it's negative, then of course you would have an elliptic equation also. Okay, so I need this condition for the system. This is a necessary condition for the system to be hyperbolic. So beta 3, so eta is positive. So beta 3, kappa is also positive. These are the transport coefficients. So this is equivalent of saying that gamma 2 should be larger than 1. Okay, so in particular, the choice gamma 2 is equal to 0, which corresponds to the original, like the unmodified Chapman-Enskog method I showed you yesterday. This would yield an elliptic equation instead of a hyperbolic equation. So instead of a wave equation, you would have an elliptic equation, which is ill-posed. Okay, so that would certainly be a necessary condition that gamma 2 is larger than 1. Also, you see that if gamma 2 is larger than 1, then beta 3 is positive, and then this friction term that you have here will have a good sign. So this give you damping, so that's a good news. Now for causality, so because eta beta 3, that will be basically the propagation speed squared. So, and we are working in units where the speed of light is 1. So for causality, then we would need this additional condition, eta beta 3 should be also small or equal to 1. Or in other words, gamma 2 minus 1 should be larger than eta over kappa. Okay, and now this motivates like a nice choice for gamma 2. It's certainly not the only possible choice, but so what you can analyze, for example, from this Hartz-free expression that I told you from kinetic theory last time, that eta over kappa goes like 1 over the temperature when the temperature goes to 0. So when the temperature goes to 0 here, this fraction, I mean, this ratio blows up. So it means you cannot choose gamma 2 equal constant, okay? So you have to choose this as a function of the temperature. And then a nice choice, because when the temperature goes to 0, the enthalpy goes to m. So convenient choice is to choose gamma 2 is the enthalpy over kBT. Okay, although this you can also write as 1 plus the energy per particle over kBT. So this is actually always larger than 1 if the energy per particle is positive. And then this certainly satisfies this condition for causality, or for the vorticity evolution. Okay, so that gives you a very good hint of what you should do, and we're going to see that this is one of the key conditions that you need. Okay, so to further analyze the system, so now we go back to this linearized system, and we take a Fourier transform in space. So all the gradients are replaced by multiplication by ik. And you see, well, of course, this is still second order because we have here terms which are of the order of k squared. But you can reduce this system to a first order in k system by introducing this new variable. So you see, you would like to rewrite this last equation as a first order equation. So what you do, you define a new, I mean, you replace v by w, which is ik, the norm of k double v, and this will be a first order equation. But of course, if you now look at the equation, evolution equation for v, this will be replaced by the evolution equation for w. So you should multiply this equation by ik, and then this equation becomes a second order equation. So to prevent that, now you replace n by ik n over n0, basically, and tau the same for the temperature. Okay, so then this equation, so this q here is no issue if you multiply it by ik. So this will now become a first order equation. And then these two equations you multiply also by ik. So here there's no problem because this k will be absorbed in w. And this epsilon, there's no problem if there's an ik in front of it, okay? So what you get then is a first order system, I mean first order in k, which will be of the following form. For u, which is now written in terms of this evolution system in frequency space, I mean in Fourier space, where u is given by the following quantities, okay? And these are 9 quantities, so 1, 1, 1, so 3 here, and then 2 vectors, okay? So it will be a 9 to 9 system. Now, fortunately, the system has some structure, so you can decompose q and w in components which are parallel and perpendicular to k, and then these two. So you get a system which I'm going to call the vector block. So this involves only the perpendicular components of q and w, and this is a 2 by 2 system. So this is really easy to analyze. So this matrix here is given by the following form. I mean, these two by 2 matrices are given like this. Okay, and now the system is hyperbolic. So to be hyperbolic, I mean, think of it that the solution of this is an exponential. It's an exponential of this matrix time t, okay? And if you want to prevent this from blowing up, to have frequency dependent, I mean, to prevent frequency dependent in time blow up, then you need this matrix M perpendicular to be diagonalizable and have only real eigenvalues, okay? And causality means that this eigenvalue must lie in the interval -1 to 1. Okay, now this is really easy to compute the eigenvalues of M perpendicular, so this is just plus or minus is here. So again, for the system to be hyperbolic, so the real eigenvalues to be real, beta 3 should be positive, and for it to be diagonalizable, also it cannot be 0, because if it were, I mean, eta is positive always. Okay, so to be diagonalizable, beta 3 should be strictly positive, and it's causal then if you have this condition here. So we cover exactly the same condition that we obtained from the vorticity perturbations. So the vorticity perturbations, they're described by this vector block essentially. So we get nothing new here. Now the scalar block is a bit more complicated. So it's a so I'm sorry. So the vector block, I mean, strictly it's a 4x4 system, because of course there are two components here and two components here, but it's like block diagonal. Okay, so this is why it's really a 4x4 block, and this is then a 5x5 block. So this is a 5x5 matrix. So that's already more difficult to compute explicitly in general the eigenvalues, but fortunately, also this block has a structure. So this matrix M has this block diagonal structure, I mean, this block off diagonal structure, if you want, where Q is given by this 3 times 2 matrix and R by this 2 times 3 matrix. And now there's a little lemma which is useful, which you can check as an exercise. So now if you form this 2 by 2 matrix by multiplying R with Q, so you look at this two matrix RQ, and suppose this matrix is diagonalizable and has only non-zero eigenvalues, which let's call them mu1 and mu2. Then you can show that this matrix is diagonalizable and that its eigenvalues are 0 plus or minus square root of mu1 and plus or minus square root of mu2. Okay, so this is very useful, because now you reduce the problem of computing the eigenvalue of this 5 times 5 matrix to a 2 by 2 matrix. And this is now easy, okay? Okay, so therefore you can conclude from this, if mu1 and mu2 are the eigenvalues of RQ, of this 2 by 2 matrix RQ, you can conclude from this that the scalar block is hyperbolic and causal if these eigenvalues are different and are between 0 and 1. Okay, and then the eigenvalues you can write, of course, in terms of the trace and the determinant of RQ. And then you can reformulate this condition by saying that the determinant should be between 0 and 1, and the trace should lie in this range. And once you realize that, so now if you compute the determinant of this 2 by 2 matrix and its trace, you get the following expressions here. So you get this expression and this expression here. And then it's just an algebraic exercise to see that this condition is automatically satisfied if this inequality, this fundamental inequality here is satisfied. Okay, so this inequality that involves only the temperature, the energy per particle E, and the ratio between the coefficients of the shear viscosity and the thermal conductivity. So it does not involve the bulk viscosity nor this parameter gamma 1. Okay, so this is for the choice gamma 2 that we had fixed before. Okay, now the statement then that this system, this linearized system is hyperbolic and causal if this inequality is satisfied and gamma 2 is fixed like this. Okay, so certainly there might be more general possibilities to choose gamma 2, but certainly this is a sufficient condition for hyperbolicity and causality. Okay, and now you can ask, well, is this a reasonable condition? And at least for the simple gas, where you know explicitly what this, I mean, there's a simple gas with the hard sphere interaction, I should say, then you know explicitly what all these quantities are, and then you can just plot this. So this is on the left plot. I show you the left-hand side of this expression. Okay, and this is this black line here. The gray line is for the equivalent two-dimensional problem, but we are working in 3 dimension. And you see this is really this stays even away from 1. Okay, so this is satisfied for all the temperature. You can compute the asymptotics for t goes to 0 and t goes to infinity analytically, and you will see that they converge to values which are strictly smaller than 1, so you're safe. On the right-hand side, I show you the corresponding characteristic speeds. So in units where the speed of light is 1 again. And again, you should look at the black curves. So there are some that propagate with 0 speed, but the non-zero speed, so they are given by this black solid and dotted lines, and dashed and dotted lines. And you see that yeah, in fact, it is causal. So it does not approach even the speed of light. All right, so so that's for the linearized system around this equilibrium configuration. Now you can upgrade these results to the nonlinear case and show local in time well-posedness. So for this, you need to do a little bit more of work. So the way we showed this was to rewrite now this, going back to the original system, and rewrite it as a first order quasi-linear system of the following form. So this is now first order in time and in space. Okay, so it has this form, and the fields now is also, to do that, to achieve this, you have to add additional fields, and the idea is very similar to what we did in Fourier space, only that here we do it in physical space. So we introduce the gradient of the particle density, the spatial gradient, as an additional fields, the same for the temperature. And then we also added the spatial gradients of the velocity field, so b mu nu. Okay, and this has information about the vorticity. I mean, the antisymmetric part would be the vorticity. The symmetric part would be the symmetric traceless part would be the shear, and the trace part would be the expansion. So we get evolution equation for those along with the other quantities. Okay, so this is a huge system, and then you look at the principal symbol. So you dot this a mu with k, which is a covector orthogonal to u, or which has u in its kernel if you want. And then you prove that the system is strongly hyperbolic. So that means that there exists a family of positive definite matrices, of symmetric positive definite matrices, H of k and u, which depends smoothly on k and u, such that if you multiply this principal symbol to the left with H, this is symmetric for all covectors k orthogonal to u, and all fields, at least in the neighborhoods of some point. Okay, and then the idea is you use standard PDE theorems to prove well-posedness in some Sobolev space. So there are two complications to this. So the first complication is that this system, as I wrote it down, I copied it here again. So this first order quasi-linear system is not directly in PDE form, because the dot is not really I mean, the time derivative is really the directional derivative along u. but then the more, I mean, this is not really a problem, but then this d mu here, so this is the derivative operator orthogonal to u. So this is again a directional derivative. Okay, I mean, you could write it directly. You could translate this in PDE forms if you could find a foliation where this d mu operator would be tangent to it, but this is not possible in general because this would mean that u would be orthogonal to these hypersurfaces, and this would mean that the fluid would have zero vorticity. Okay, so certainly you don't want to, I mean, that's too restrictive. Okay, so you cannot assume that this is actually purely spatial derivatives. And the second complication is that by rewriting the system in first order form in physical space, of course, you introduce a lot of constraints. So for example, there's a constraint associated to the introduction of these variables. At the end, you should check that n mu really is the gradient of n over n to map it to a solution of your original system. And likewise for these other new fields that we introduced. Okay, so one has to check that this new field they propagate, I mean, these new constraints associated to these new fields, they propagate correctly. So the first issue is dealt with by using a more general notion of strongly hyperbolicity, which doesn't depend on any foliation or any coordinates, which was given in a paper by Oscar Reula. And then you just write the system as in space-time. This quasi-linear first-order system in space-time, and then according to this definition, this is called strongly hyperbolic if there exists a covector field, so that the principal symbol in the direction of this field is invertible. Okay, and such that for any covector omega transverse to n, you have this condition here. I'm sorry, this should be a omega and not a v. Okay, so basically, if you take this transverse covector field and you add to it minus lambda n, okay, so and then you kind of sweep through all the possible lambdas in. Okay, so you can think of this as this is a line. I mean a line which will be transverse to omega. Okay, and now you take the union of all the kernels. Okay, of this. Okay, and this should, if you take the dimension of this, so this should precisely give you the dimension of the system. So m in this case. Okay, so now, of course, you can rewrite this system here. You can write it in trivial in this form. But now the nice thing is that this definition here, this is stable with respect to n. So you can show that if you perturb this n a little bit, then this condition will still be satisfied. Okay, and this is something that we use so that we can show that this definition of strongly hyperbolic I gave you before is actually equivalent to the definition of strongly hyperbolic that you can use for PDE standard theorems. So the second issue is treated by deriving evolution equation for the constraint variables and checking that this system has only the zero solution for trivial initial data. Okay, so to each of these new fields, so constraints variable will be, for example, n mu minus d mu n over n. Okay, so this is a constraint. This should be a variable which should be zero, and then you derive an evolution system for it and show that it satisfies, again, a strongly hyperbolic system. So it has a unique solution. And the system is homogeneous, so it has zero is the only solution. Okay, so let me formulate now the result we get from that. So assume now that the space-time, so remember, we're not solving Einstein's equation. We just assume here that space-time is given to us. Now let's assume it's globally hyperbolic and foliated by Cauchy hypersurfaces. And for simplicity, I assume they are compact. Then definitions, or an initial data for our system is a choice for n, t, u, e, and q. on a given hypersurface, such that n and t are positive, u is future-directed unit time-like, and q should be orthogonal to u. Okay, and then we assume regularity conditions, or NTU should be in HS plus 1 and epsilon and Q in HS. So the reason why there's this disparity between the regularities that when we write down the first order systems, they involve also first derivative of these quantities. So that's why this is assumed, okay? All right. And if gamma t is asymptotically flat instead, then one requires NT and U to converge sufficiently rapidly to constants and ask similar regularity condition. Okay, and then so what you can show then is that now assume that in your systems or E, so the energy density, so the energy per particle and the transport coefficients and this gamma 1 are C infinity functions, strictly positive of the temperature. And they fulfill these bounds. Okay, so for the heat capacity at constant volume, which is the energy, the derivative of AE with respect to T, and assume that gamma 1 does not cross 1. So either it's smaller than 1 or larger than 1. Okay. Should make the choice for gamma 2, we found H over KBT, and assume that this fundamental inequality is satisfied. Okay, for all t. So this is a condition on these functions, on these functions here. Okay. And then there's another technical condition that we need. So we assume that the non-zero characteristic speeds are distinct from each other, all temperatures. So this is certainly satisfied for the simple gas. And take an initial data sets, and then you can say that there exists a time to the past of T0 and a time to the future of T0, such that the fluid equation have a unique solution on this submanifold. And if you slice gamma T between T1 and T2 with the specified initial data on gamma T0. Okay, moreover, this solution depends continuously on the data in the space in the subbolus space I told you before. Okay, so this is the theorem that shows you that at least you can compute. I mean, you can evolve at least locally in time your initial data. Okay, so now I'm going to move to mode stability. So first of all, are there any questions so far? So if not, so let me then go on with this with mode stability. So now let us come back to the linearized system, okay, which describe linearized, the linearization of the global equilibrium configuration. Okay, and now let us look at all possible mode solutions which are of the form. So the solution of the form like this. So u of t is e to the st u0. Okay, and then that means that S, of course, should be an eigenvalue of this matrix P. And now the challenge is to show that the real parts of these frequencies is negative for all possible wave vectors k, except for k equals to 0. So one has to analyze the roots of the characteristic polynomial, and again, because the system decouples in the scalar and vector blocks, one can look at each block separately. So in the vector block, this is a 2x2 system, so here it's easy to compute the modes explicitly. And here's the expression for this frequencies. I mean for S. So so it has this form. And then you see by inspection that this is satisfied. Okay, so if k is different from 0, then this is all the real part of this is always smaller than 1. So there's a -1 here, and then if k is small, then this what is under the square root is always smaller than 1 magnitude, and if k is very large, then this becomes imaginary. but in any case, the real part is smaller than 0. Okay, and now you can think of it, what happens to these hydrodynamic modes, which is really really this theory makes sense, at least how we derived it from the Chapman-Enskop approximation for small Knudsen numbers, and that translates that the mean free path times k should be small. Okay, and here this transport coefficient, there will be of the order of the mean free path. So if you look at this regime where this theory really makes sense physically, then you find then this reduces to this following two. Okay, so you have a mode that decays and goes like minus k squared. There's some higher order correction, and these are called the shear mode. So this goes like L, the mean free path times k squared. And then if you choose a minus here, then this mode goes like this. And this decays much more rapidly than the first mode. And you see it because it has this kappa, the transport coefficient here. So it goes like 1 over the mean free path. Okay, so these modes will be rapidly damped. In the scalar block, the system is more complicated. It looks like this 5 times 5 block, but now it's not, it doesn't have this block of diagonal structure as before, because you include the lower order terms. I mean, so now you get a fifth order polynomial for your characteristic polynomial. So you see from this expression immediately that if k is 0, then the solutions are 0, and you have two negative solutions. So h0 and h1 are given by these expressions, which are positive. And if k goes to infinity, you can show that s over k converges to I times the characteristic speeds we find previously. Those are so s go. I mean, the system becomes purely oscillatory in these limits. Okay, this because it is hyperbolic. Now you can again look, and that's what's interesting for physics. What happens if for small values of the mean free path times k, and here you find different kinds of modes, but all of them decay. So you have mode that go like minus 1 over tau. So tau would be the decay time. And then some of them oscillate. And then you have higher order corrections. And then you have some rapidly damped terms, which go like 1 over the mean free path. And then you have again shear waves, you have heat diffusion modes. So these are solutions that are known from the physics literature. And then you have the acoustic modes. So the acoustic modes, they have the propagation, which is given by the speed of sound, which is given by this expression, but they are damped when you take into account the dissipative effects. Okay, and you can actually compute this damping coefficient. Okay, now the question is what happens in between. So imagine this is a complex S-plane. So we went for stability, went everything to be on the left-hand side. So we know when k equals 0, we are on the imaginary axis, but we are when k becomes positive, it goes in the correct direction. Okay, so this is what the calculation we just looked at. And we also know that k goes to infinity, then it will again somehow asymptote to the imaginary axis, because s over k goes to some imaginary number, purely imaginary number. But the question now, what happens in between? Okay, so could it be that if k goes from 0 to infinity, that somehow you cross the imaginary axis? And what you can show is that under appropriate conditions, the answer is no, so it doesn't cross. But for this, we need to make a lot of assumptions, say on the thermodynamic parameters. So first of all, we need the energy. I mean, all of them are quite reasonable and satisfied for a simple gas. So the first one says that the energy density should be an increasing function, which starts at m and goes to infinity. Then the second condition is that the heat capacity at constant volume should converge to positive values when t goes to 0 or infinity. The speed of sound should satisfy inequality. And then there is some requirement on the boundness of some coefficients. And then the important thing is that gamma 1 should basically be chosen large enough. So remember, gamma 1 we hadn't needed yet for the hyperbolicity, so this was still completely free. And if you choose it 1 plus this complicated expression, but lambda 0 here is a constant, so you can show that if this constant is large enough, then the scalar block will be stable for all temperatures and all k. Okay, and the proof is not very elegant, but it uses this Hurwitz criterion, which allows you to show that a certain polynomial is stable if and only if certain condition on its coefficients are satisfied. So in this case of the fifth order polynomial, all these coefficients here should be positive, and then these three determinants here should be positive as well. And then one has to carefully check that all these conditions are satisfied. And this is how this is proven. Okay, so this establishes the mode stability of the problem. And now let me finish off with some brief remarks regarding the entropy production. So remember that in the Boltzmann case, there was this entropy flux, which you could compute from the distribution function. And Boltzmann equation would imply that the divergence of S is larger or equal to 0. So the question is, what happens now to the truncated first order fluid theory? Okay, so can you still construct an entropy flux, and does it still satisfy this condition here? Now, because this theory was derived from kinetic theory, so we can use, again, kinetic theory to derive an expression for the entropy flux. So what we do, we plug in this Charpin-Enskog ansatz we had. So this was the local equilibrium distribution function plus epsilon correction. Okay, so you plug this into this f log f, and you expand in epsilon. So you expanded, you plug this in. So when if I integrate over p, then this 0 order contribution will just give me the entropy of the local equilibrium configuration we had already calculated. So this is this term here. And then this term, because again, you know what F0 is. So this is some constant, and the log of it is some constant times U alpha P alpha over KBT. Okay, because the F epsilon was essentially the exponential of this. Okay, so if you take the logarithm, this is what you get. And if you integrate over P, so you plug this in here. So the first contribution, so this multiplied with H. Okay, so the term that is linear in P, when you integrate, will give you 0 because of this this condition that we put that the first 5 moments are 0. And then the one that is quadratic in P, that will give you a contribution from the stress energy tensor associated to H epsilon. Okay, so this is what you get. And now the interesting thing, you can show that this is actually up to this quadratic order. This exactly coincides with what is called the Israel-Stewart entropy in the literature. So the Israel-Stewart entropy is given by this expression here up to first order. So mu here is the Gibbs potential. So this is the enthalpy minus Ts. Okay, and you can check that this expression reduces to this one up to epsilon squared terms. Okay, so and now, so what you can do, you can compute the divergence of this Israel-Stewart entropy. So these are now our candidates. So this is because it's reduced to something known. So this is what you're going to take for entropy. And if you compute the divergence and you use a balance law, then you get the following expression. And check it as an exercise. Okay, and now you see here appear this off-equilibrium contribution. So if this off-equilibrium contribution are zero, then you will get exactly zero as it should. But now you have to plug in the constitutive relations. Okay, so you have epsilon, q, and tau. And if you do this, then you see you get so you see these terms that don't have the gamma, these are exactly the same combinations that appear here. This one will correspond to this here, and this one to this here. Okay, so the contributions that are independent on capital gamma, they give you the first line here, and you see this is quadratic. So this, and remember these transport coefficients are strictly positive. So this is a positive definite. However, there's some cubic corrections, okay, that vanish if gamma 1, gamma 2 is 0. So why are they cubic? Because remember that this combination here, because of the Euler equations, I mean, because of the balance equation more precisely, they are second order in the gradients. Okay, so that's why these are cubic in the gradient. So what happens is that you get this quadratic term, which is positive definite. And if you could choose gamma 1, gamma 2 equals 0, you would have exact non-negative entropy production. But it turns out you cannot have it both ways. So if you put gamma 1, gamma 2 equals 0, your system is not hyperbolic. If you want your system to be hyperbolic, you need to choose this differently. Then you will have this cubic term. So your entropy production will not be exactly non-negative. However, to the validity of your theory, given by this term, so up to this order, you are okay. Okay. All right, and I think this is the last slide, so I finish here.
Um, so thank you very much for these lectures. Are there any questions from the audience?
I will have a question.
Yes.
So when you were looking at the full system, so I mean like the first order system, but not the linearized version, and you were proving the hyperbolicity via showing that it's a strongly hyperbolic system.
Yes.
You mentioned that there were some symmetrizers. Are these symmetrizers explicit, or do you just know that you can construct these in principle? And also, like another question would be, so do you know something else besides mode stability about the long-term behavior of the system?
Okay, so regarding your first question, so we can, what we know how to construct is we can construct a K dependence explicitly of these symmetrizers. And then we could in principle also construct the symmetrizer completely explicitly up to linear algebra. So we would need to look what are the, it's like constant matrices that diagonalize these scalar and vector blocks. So in principle, we could compute them, yeah. But at least a K dependency we know explicitly, so we can check that they're really smooth in K. Regarding to your second question, so I'm afraid no. So far we haven't. Well, just because we didn't have time to look at it, so we don't. I mean, certainly for this system that I mentioned, we don't know anything more than mode stability.
Thanks.
All right, so if there are no other questions, let's thank Olivier again.